series. He is a PhD candidate at CMU, and he's joining us today with a few other CMU folks. Noelia Gutierrez, who leads the Design Research Collective lab at CMU, and sorry, the opposite, the Biosim lab at CMU, and Chris McComb, with whom we've worked with before, and it's how this research connection came about, who leads the Design Research Collective at CMU. So with that, it's a short meeting. It's a short 45-minute meeting. So Wenzhuo, I'll hand it off to you.
All right. Thanks, Daniel, for the introduction. And thank you, everyone, for being here with this talk today. I know it's quite early in some part of the country. Well, I'm currently a third year. Can everyone see my screen, Daniel?
Yeah.
Yes. All right.
Yes.
So I'm currently a third year PhD at Carnegie Mellon, advised by Dr. McComb and Dr. Gutierrez. And today I would like to share with you about some of our work in trying to advance machine learning in large-scale engineering simulations. So I guess the first question to ask in this case is why machine learning, especially in such a rigid and safety critical scenario as engineering simulations? Well, I guess the answer is when we talk about real world engineering models, we're actually talking about different levels of dynamics, and such can differ based on their good sizes, ranging from advection, seen at the top level, and then diffusion as we travel further down the length scale, and finally at molecular distance, maybe reactions that we can see. And those are also reflected in our grid sizes that we select for different types of simulations also, as we select larger grids for eddies and smaller grids when we want to characterize energy cascade, and even smaller down to Kolmogorov scale when we want to categorize energy dissipation. Now, the problem here is as we want to characterize and resolve for finer and finer details in engineering, we actually increase our computational cost. And as this research study shows here, this kind of increase goes at exponential scale. Sometimes it can get even more extreme and range up to cubic, as some research have proven that with a 10-fold increase in Reynolds numbers, there comes with a 1,000-fold increase in the computational cost that we have seen. Luckily, most engineering simulation scenarios that we see today are actually a combination of physics and data. When we run into larger length scales, the physics dynamics that we see, we often understand more about them, that we have a much more completed and well-known PDEs to solve for them. But as we travel down to those subtle areas that we might know less about, we use some kind of data to compensate for that kind of information loss. And in this case, many data-driven models are being introduced as they're proven to be more efficient and robust than numerical solvers in many cases. The first research I'm showing here is actually done by Harvard. And what they found is that using a machine learning model to compensate for numerical solver at subgrid scale, they can actually achieve an 86 times speed up in computational speed without compromising the accuracy of the spectrum information. And also another research have been proven that physics-informed machine learning models are actually more robust towards noisy data and uncertain inputs. And that highlights actually their application in things like even like stochastic physics systems. Numerous research have also been done in this field. And based on their approaches, I would like to classify them into 3 different categories. One being physics-informed machine learning that introduces certain types of learning bias into the physics system by penalizing for a specific loss function direction. One being operator regression models that introduce a certain type of inductive bias by carefully structuring the network model to approximate the behavior of a partial differential equation. And finally, learned correction methods that introduces observational bias by integrating a machine learning model with a numerical solver to accelerate the speed. However, with all the aforementioned efforts, we still rarely see the applications of these different types of methods in engineering simulations. And of course, there are a wide range of discussions about why this happens, but at least from our perspective, we see the major challenges as follows. The first one being challenges with mesh-based simulations, where we face this kind of transition in data modality and fidelity from what a machine learning model can commonly accept and learn to these kind of highly variant meshes and geometries that we see in modern engineering scenarios. Now, this will also account for these kind of varied boundary effects. And when I say boundary effects, I mean both geometrical, means the shape of the simulation that we're getting into, and including, of course, sometimes internal obstacles, internal boundaries, and also these kind of highly varying boundary values as taken as input to our engineering simulations. Also, there is this gap between hardware limits as well. Although machine learning models, they're highly computationally efficient, their computational complexity, as is shown here, still follows this kind of power series law. And as we try to take as input those engineering simulations with hundreds and thousands or millions of elements, eventually they're going to encounter these kind of unbounded memory leakage, as the recent research has already proven that for some neural networks, especially for graph neural networks, you're going to face this kind of unbounded memory leak at certain points of the computation. And finally, a bit hard to solve than all of the previous problem is the lack of confidence that we as engineers probably have for machine learning models. Suppose we have a prediction result from an engineering simulation domain from a physics-informed machine learning model. Do we know if we can trust those? So based on all these issues that we have identified, or these kind of gaps that we have identified, our work at CMU aims to achieve two parts, advancing in physics-based machine learning, one being improving the flexibility of physics-based machine learning models, and then another being improving the scalability. And combining these two, we hope to achieve more applications of machine learning in actual engineering scenarios. And by flexibility, more accurately, we're describing the network structure design of machine learning models to learn for unstructured physics data. And for scalability, we want to overcome these kind of inherent hardware and capacity limits of machine learning models in large scale and multi-physics simulations. So to address the flexibility issue, what we're talking about as the previously mentioned issues are two major points. One is, how do we account for various boundary effects, and how do we make machine learning models geometry aware? Now, for this, I would like to introduce the super resolution method. Those are commonly seen in image processing techniques, but if we want to talk about something more physics related, it actually means different things. It means that we're solving for some length scales in our physics system, and we're compensating for the rest of the length scales with a machine learning model. The benefit of this is that we have a numerical solver to account for all those variant boundary conditions, while the machine learning model can focus more on recovering the dynamics inside of a system where it is probably most good at. To address these kind of variant geometries that we face, we turn to graph network structures, as the unique property of such a graph network connection can make this kind of one-to-one mapping between a physics and geometry mesh space into a topology structure. Now, this will allow us to preserve physical, geometrical, and connectivity information all at once, making the prediction of our machine learning model to be directly integrated with a numerical solver. And note that the benefit of such a data structure can be seen from our shown examples here. If we're using a matrix, essentially we can't see clearly how these kind of dynamics is varying between a low resolution simulation and a high resolution simulation. And most of the previous work we're seeing in this field are based on these kind of matrix-based representation and downsampling technique to create their low resolution samples. And that naturally is problematic, as we can't kind of recover these type of missing dynamics as what is actually happening inside our numerical solver. So how do we try to recover these kind of missing dynamics based on our neural network model? Well, we refer to what is typically done in numerical simulations, accounting for those kind of discretization errors between fields. Now, numerical errors can generally be decomposed into three different elements. The first one being the roundoff error that basically states this part of error comes from the truncation of our hardware, including CPUs and GPUs. They all have their own numerical precisions. The iterative error that originates from our iterative solver, that is also what's commonly used in an engineering simulation scenario. And finally, the discretization error that accounts for, because we are solving for a nonlinear partial differential equation system. And this kind of differences in our solvable grids are naturally going to cause some kind of error that no matter how much iterations we do, are unable to resolve on a lower resolution grid. And discretization error, commonly in traditional numericals, are described by this kind of power series approximation, which basically states that the discretization error field is a power series of the discretization size or the mesh grid size at every specific geometrical location. Now, this kind of estimation is very good and very accurate for global properties such as drag coefficients, lift coefficients, weight and area of certain geometry. But if we account for localized properties such as speed, velocity, and pressure, what we might care the most about in engineering simulation scenarios, such power series law are going to give you highly nonlinear behaviors. I guess that is also kind of expected. So naturally, the question is, since machine learning models are designed to account for such nonlinear behaviors in various types of systems, can we introduce the use of machine learning approximators for discretization error? This is actually our development, and we start from writing off, for example, if we want to estimate this discretization error at any center node, we start by writing off such error that's associated with every edge that is surrounding it. And then we average out the nearby edges error on this center node and define it as the discretization error at each specific geometry location. And finally, we turn this into an approximator by adding linear transforms and nonlinear activation functions so that this entire structure can be learned. This seems to be a very straightforward process, but actually we can prove that such structure, once derived, can approximate any function up to an arbitrary accuracy, as is shown in most machine learning models. And essentially, if you do some kind of mathematical tricks into it, you can able to exactly resemble this with the commonly seen ResNet, only that this is kind of a more advanced version of it with more power series on the activation functions. But if we do some mathematical tricks and restrict the order of summation and stuff, it's going to be reduced into a ResNet expression. So the proposed network structure looks like follows. It's a graph-based geometrical aware super resolution network that we call the Taylor series expansion because it originates from this kind of series expansion error correction network, or TEACnet. As if we take into a mesh-based geometry simulation with both geometry and physics information, we process such information separately by passing them through an encoder series, and then pass them through layers of TEACnet kernel that does error correction on the final and sum it with the residual connection from the previous encoded physics properties to make the predictions and that can be interpolated onto a higher dimensional mesh. And for each of these TEACnet layers, it's basically composed of the previous mathematical expression that I just shown on the previous slide as we process physics and geometry information. In this case, that will be the node embeddings and edge embeddings of a graph kernel network. Those are processed separately and exactly replicates the mathematical expression that is shown in the previous slide. So with this, the entire workflow looks like we take in a low resolution mesh along with boundary conditions and physics equations pass them through a numerical solver, which is self-implemented, we can get to some kind of intermediate result. That's one of the low resolution, but accounts for the previous set boundary conditions. And then we map the the intermediate result along with our desired output mesh into the machine learning model, which in this case is thicknet. And we're going to get a mapping of the high resolution output based on our intermediate result and desired mesh output. We conduct numerical experiments on both structured and unstructured grids. And in this case, for structured grid, of course, there are a variety of multi-physics scenarios that we conduct, but I'm only going to show two here, one being the Burger's equation. And the unique thing about this is basically this is a reduced scenario of the Navier-Stokes, and it creates this kind of very sharp wavefronts as it travels, and that poses a unique challenge for machine learning models to learn, as those have very high gradients at the wavefront end. And secondly, is a very common problem that we see for unstructured grid. That's the Navier-Stokes equations with the cylinder wake problem, where you're going to witness this kind of development in the von Karman vortex street and various dynamics that can be seen based on the difference of the grid sizes. We demonstrate the prediction of model performance on Burger's equation, where we are able to achieve an up to 8 times resolution increase on each dimension. And you see how thicknet is able to correct for those sharp edges that are not well characterized on a low resolution simulation. But we also have well-controlled maximum error at wavefront and a very nice error distribution across the entire domain. The same story can also be told for Navier-Stokes equations, but in this case, since it's an unstructured grid, we're going to see the prediction of thicknet actually accounting for these kind of internal boundaries. Although it is not specifically instructed to do so, we see the flow is actually very nicely going around the internal obstacle and replicating some kind of missing dynamics that is not seen in the low resolution simulation, including the maximum error divergence. We perform certain types of generalization tests, and we are able to show that for various different types of models that we train, we're able to actually follow the L infinity that is the maximum error divergence of a numerical solver across various resolutions, even generalizing to those resolutions that we are not trained upon. Now, this actually gives us confidence when we want to apply this kind of super resolution network to any arbitrary resolution that is not seen in training, because we know that in this case, the error is bounded and it will highly replicate the performance of a numerical solver in this case. What about other models? Of course, I mean, neural operators, they can obviously perform these certain types of tasks as they have a much more complicated kernel, and they can be trained to fit this type of purpose. In fact, we have already seen many other literatures that are using operator regression models for super resolution tasks. But our method, by introducing a designated inductive bias by penalizing the underlying model structure to be something like a power series expansion, we are able to reduce the learnable parameters by over 30%. And that results in a computational cost reduction on CPU inference, for example. On 48 cores, we're able to reduce the computational time by 42%. And the reduction only gets even further as we further limit the amount of available computational resources. And we're also able to see the difference in the learning process between our specifically designed mesh-based learning correction and those learning process of a neural operator. And we're going to see how thicknet is starting from a randomly uniformly initialized error distribution and gradually learning based on the edges and their associated errors to generally approximate the final solution, while neural operator does obviously operator regression scenes. Now, till this point, I would like to switch gears a little bit, and because all of the physics scenarios that we've seen so far are still those kind of very small rectangular or even unstructured grids. But even for unstructured grids, we're dealing with stuff like 1,000 elements at most. But if we turn to a real engineering simulation, what we've learned so far would highly likely look something like this, where we have a complete transitional boundary turbulence layer of over 7 million nodes. But what we're able to see at this point is only a very, very small portion of it. Moreover, for these type of physics scenarios, we're going to see highly variant dynamics, including free flow isotropic turbulence, a laminar boundary layer that occurs as the flow impacts with the boundary at the front end, and mode 1 and mode 2 turbulences as the boundary layer turbulence gradually develops. So to solve this, naturally, since we're able to compensate for a very small region inside this, what about doing domain decomposition? And such is a very well-studied concept in CPU parallel computing, but not so much for GPU computation at this point. And we're able to see that current physics-based machine learning works, few of them actually demonstrate their ability in scaling up to any indefinite size. And the question we want to raise is that, is it possible to improve the spatial scalability of machine learning models, especially physics-based machine learning models, without sacrificing its stability? A very typical example of this will be what's happening, for example, for this neural operator model on a atmospheric prediction task, as we scale the prediction domain up to the entire Earth. And you're going to see the divergence in these white boxes as the predictions are actually not trustworthy from an engineering perspective. The way we approach this problem, same as what we kind of always do in our own research, and it's also a method that I personally prefer, is to refer to traditional analysis inside a rigid physics-based system. And actually, I found this, it's called the principle of locality in physics system, basically states that when we are doing a finite element simulation or any physics-based computation, points that are closer to one another will have a stronger coupling than points that are further away from one another. This is actually very easy to understand, as the transport of information in any physics system cannot exceed, in the more general case, the speed of light, but for any material transport system, that speed is actually a priori given as a global property during our simulation. Also, this means that the causal structure of space-time is also a priori given. This might seem to be a really conceptual thing, but we actually use it all the time in our finite element simulations. And for example, this can be expressed as the upwind numerical scheme, or the CFL number, that states that to solve for the physics information at the next step, we only need the information from the previous 2 nodes or 3 nodes based on the accuracy of our numerical scheme in the upwind direction. And this is for traditional finite element simulations, but for more advanced spectral solvers that solves for the spatial temporal information of a physical system at the same time. This is a very newly proposed method just out in 2023. They say that in their implementation, they actually rigidly enforces this kind of sparsity in their relation connection matrix, where only the diagonal terms and 2 off-diagonal terms exist, and all the other terms inside the sparsity matrix are 0. Now, this means that only 3 adjacent points, only relationship between 3 adjacent points are considered while solving for the entire spatial temporal information of a given physics system. So since we only need 3 adjacent points to solve for everything in traditional physics, do we need the information from an entire data grid to make the machine learning model learn efficiently what is the dynamics existing in our physics? Well, I guess this comes with a controversy. It's quite controversial, as when we try to increase the approximation ability of a neural network by inserting more and more layers, we're going to increase the dependency area in our original data grid. And that dependency, actually, the size of that dependency actually increases in a linear scale if we do some bit of mathing to it. But does that also introduces some kind of irrelevant and noisy information into the training of the neural network system? To test for this, what we are proposing is a localized domain decomposition that applies some kind of clever decomposed and reconstruction methods to make sure that the machine learning model only has vision to a certain area of data. And we carefully control the method by which we decompose and reconstruct them to make them consistent and learnable across the entire physics field. The natural things to consider here is how much points do we need to make the machine learning model effectively learn for the physics dynamics. If we give it too much, it might include some kind of noisy information. If we give it too little, then the machine learning model will probably not be able to train at all. And how do we ensure that since this is a decomposition method and everything is computed in parallel and concurrently, how do we ensure that physics properties are still continuous at the boundaries? Now, to answer the first question, for traditional physics, we would turn to CFL numbers that's dependent on the transport of information. But for machine learning models, since we're considering everything from a functional perspective, what we're doing here is investigating into the effect of frequency leakage caused by our windowing and also discrete Fourier transform that will cause certain types of frequency leakage as well. Now, what we want to show here is that to be able to fully recover the frequency character, the number of nodes to include in a localized region must satisfy this expression that tells this kind of combined relationship between the size, the optimal domain size, the mesh size of the simulation that we are accounting for, and also the frequency bandwidth of the physics properties. You're going to notice that this expression actually looks very similar to the Nyquist sampling theorem in signal processing, and that might tell this very interesting relationship between physics-informed machine learning and signal processing theories. To make sure that the boundary information that we are learning is kind of also consistent, we utilized this trick that's introduced, also a very recent work, that is introduced by separating the learning of the source term and boundary influence inside a certain partial differential equation. And we're going to see that by separating these kind of learning separately and make the machine learning model actually be able to compensate for a certain level of boundary influence. I'm not talking about like a lot of boundary influence, like specifically inserted Dirichlet or Neumann boundary conditions, but just by learning these kind of little subtle boundary influences is already sufficient to make these kind of decomposed machine learning models significantly more stable in terms of temporal stability as we do recurrent predictions in time inside our temporal horizon. We conduct numerical experiments on fundamental physics scenarios, Berger's equation I have just introduced in the previous test case, but also mass transport that allows us to actually control the frequency bandwidth to test our theory about how the machine learning model will react to different frequency components and their relationships with the mesh size. But these are all stuff that are like previously seen. What is not previously seen is this kind of highly complex physics scenarios that can also often incorporate millions of elements and various range of dynamics. What we are able to show here with at least more specifically the isotropic turbulence case is that applying domain decomposition methods actually make the machine learning model learn better. And by learn better, I mean both in terms of generalized mean squared error across the entire field and also the localized maximum divergence at specific geometrical locations. And also, we're going to validate our theory that actually it's not that the more data the better, as in the figure B here, there is actually an optimal window size for this type of problems. And in this case, the window size is about 14 nodes on each dimension side. And as we gradually increase the learning window of our machine learning model, we actually see decrease in the model performance, meaning that for this specific physics-based use case, it's not that the more data we include in our training, the better the machine learning model is going to be trained. And this is also validated if we actually compare the training and testing curves. And we're going to see that decomposition actually improves the convergence property for all machine learning models tested, although it is kind of specifically designed for operator regression models. But for physics-informed convolutional neural networks, for Fourier neural operators, for deep O-nets, and for distilled rest nets, we all see significant improvement in training and testing convergence for both mass transport equation, Burger's equation, and even more complicated isotropic turbulence. Now that we have demonstrated for these kind of uniformed physics scenarios, we see improvements. How do we characterize physics for more complicated stuff like transitional boundary layer, where in this case, you're going to see that if we take a very small sample of physics at different geometrical locations, you're going to see this kind of highly variant energy spectrum at these kind of decomposed locations, indicating that probably since energy spectrum denotes the distribution of physics dynamics inside our domain, probably they compose different underlying distributions for machine learning model to learn. And this in turn gives us a thought about some kind of transfer learning, because we have a generalized model that learns for physics dynamics, for example, Navier-Stokes equations, but the subtle difference inside turbulence and laminar flow are going to be different, as is shown by the energy spectrum here. So we're proposing this kind of adaptive domain decomposition network where we do some kind of characterization of physics at the front end, and then we classify them into different composed subdomains, and then are assigned to various transfer learning models that are specifically designed and adjusted to handle those specific types of physics. And what we're seeing here is that we're using traditional PCA or energy spectrum encoding that are really computationally efficient and shouldn't take too much time to do this kind of classification, while the parallel mechanism still stays the same. And we actually present a sample prediction of this framework right here with isotropic turbulence of over 1 million nodes. And you can actually see how this kind of adaptive method is trying to correcting and minimizing any error that's apparent in any localized region by this kind of little black boxes in the absolute difference plot. Now, if we actually apply it to this complicated transitional turbulence scenario, we're going to see that although very interestingly, all the methods that we propose to characterize the physics in in aforementioned manner that's completely irrelevant to the actual physics dynamics itself, all the characterization are statistic-based, but they're still able to distinguish the physics and assign essentially 3 different machine learning models to 3 different physics dynamics, including, for example, here, model 0 characterizes for the laminar flow, and model number 1 characterizes for some kind of transitional behavior between laminar and turbulence. And we have another model that is currently applied for the isotropic turbulence scenario. And we see generally very well controlled error distribution across the entire field, ranging from isotropic all the way down to laminar, and also 3 different variantly tuned models accounting for laminar, boundary layer, and isotropic turbulence. And this is also, as I said, a fully automated process. And we're going to see that actually these kind of decomposition matter, as if we reduce the number of submodels into obviously no segment at all, you're going to see that the machine learning model is actually not able to preserve a very good and very steady temporal prediction, as accuracy drops really fast as we proceed into the temporal horizon, while appending 3 different submodels here seems to be best accounting for the underlying distribution of the data, as the predictions turns out to be the most stable. And also different characterization methods matter with regard to what the model is actually learning, as recurrent predictions show good temporal stability, although for all the different models shown here, we do see that the Wasserstein distance is producing the best result in terms of temporal stability, which might suggest that such encoding and classifying method will distinguish the data distribution better for transfer learning models to actually account for variant types of physics. And that is definitely somewhere to be explored further. Now, at this point, I hope that I've already convinced you about our methods in improving our efforts improving the flexibility and scalability of physics-based informed machine learning models, both in terms of mesh-based super resolution with graph neural networks and locality-enforced adaptive decomposition for physics-based machine learning. Now, there are still quite some time left in my PhD, and what we're going to do right next is trying to incorporate some kind of advanced boundary condition modeling. And to our specific interest, mostly it's about elasticity in our boundary conditions and probably fluid structure interactions that are currently rarely accounted for in all of the literatures that we can see. Also, we want to incorporate this kind of graph decomposition as well to make adaptive models towards multi-scale and multi-physics coupling, which might range from nano all the way up to centimeters and meters and all the way above. And by combining all of the aforementioned efforts, we hope to achieve trustworthy application of physics-based machine learning in actual engineering analysis. To give you a hint on what our current projects in trying to achieving this looks like, this is what we're actually working with Eaton Research Labs about trying to combine numerical simulations with machine learning methods. And we want to develop this kind of very powerful tool in providing fast engineering analysis during the engineering design phase with actual confidence. Now, this is actually the actual part that's inside the low pressure air duct on the Airbus A350 turbine engine. And also, because of this kind of unique ability of machine learning models to handle inaccurate measurements, and often as they are more stable than numerical methods in this case, it has the potential to be applied into scenarios where it is more difficult to get the obvious measurements for numerical methods to work. And one typical case of it is in medical applications where you tend to get these kind of very blurry and noisy MRI scans. And this is also what we're currently proposing to American Heart Association, that we can actually apply these kind of adaptive physics-based machine learning to account for these kind of noisy images and reconstruct what's actually happening inside a person's vessel. But we cannot actually accurately do that with traditional computational fluid dynamics, as the boundary condition effects, the input and output flow are all stuff that we cannot accurately measure inside the human body. And with that, I would like to thank Eaton Research Labs, ERDAC, and NSF for funding my research, and also my kind advisors, lab members, and collaborators for supporting my work. Thank you all for listening. Please visit our group website for more information, and I welcome any questions that you may have.
Awesome. Thank you so much. Great presentation. Really appreciate the time. Do we have any questions? Alex.
I have a super superficial question for you. So in the super resolution reconstruction, the various techniques you presented, they were great. It was a great overview. I really appreciate that. Generally, how are they for numerical phenomena that are very high frequency in nature? So things like shock waves or contact or bubbles or cavitation, those kinds of issues. How do you see these techniques applying to those kinds of discontinuities within low resolution fields when you're reconstructing a high resolution field?
Yeah, right. That's actually a very good question because currently I have to admit that our proposed method cannot actually account for those physics characters that are like way too high. And that's basically because what we're proposing is based on this kind of subtle discretization error corrections. And if it is not there in the low resolution physics, and there is only so much that a machine learning model can do. But there are actually methods for correcting those. And that's actually presented in one of my very first slides. Yeah, right here. So these kind of learned correction methods where they basically attach a machine learning model to act as a subgrid scale model for a large eddy simulation. And you're able to see how they're able to recover these kind of missing vortexes between a low resolution direct numerical simulation and the high resolution direct numerical simulation by attaching a machine learning model to replace for some kind of statistical part of it. But I know this is done by a computational mathematics group, and their work is like highly theoretical, and very few are actually applied in engineering simulations. So I guess this will be a very interesting future direction to explore. Yeah, that's kind of my current perspective.
Gotcha. Yeah, so would the layman's response be you can't make something out of nothing? So if there's no indication for in the low resolution flow field for one of these discontinuities, you can't just have the neural method fix it for you. You can't make something out of nothing.
Yeah, there is potential for that because if we think about large eddy simulations, essentially that is also a statistic-based method because we're using statistics to append for those subgrid scale effects. So machine learning models can be a very good alternative to those statistic-based subgrid scale models, as effectively machine learning model is also a statistic-based model, but it's kind of perhaps more advanced than those subgrid scale models that's proposed like 50 years ago. So I definitely see the potential, but there is definitely more work that needs to be done in this case.
Thank you.
Yes, Tom.
All right. Thank you, guys. Thanks for the great presentation. I should definitely go and check out your papers. I really appreciate that, this was refreshing, really, in a sense that you didn't do, create data end-to-end, training a model, and finding or doing a super resolution. You're going deep inside the model, trying to see what you can change inside the model itself. So I really like that approach. And thank you, Danny, for inviting him. So I really appreciate that. So yeah, I have several questions, but the first one. So the first part of your talk, the one that you're trying to learn the error for the super resolution, I missed how this is geometry aware, and also how is it? So if when you learn that, let's say through the Taylor series and the model that's inspired by the Taylor series, how do you make sure that's generalizable to a different, Reynolds number, different geometry, different condition? Because I didn't see anything specific to that. So essentially, you're learning the error based on the training data, and you're applying that to the same data, the flow over cylinder, let's say, right?
Yeah, so basically the geometry is learned along with the data because graphs, you kind of process the nodal and structural information separately, and we store the geometry as a set of values inside our graph edges, and those are the positions of the forward node, next node, and connectivity. And those can also be represented as this kind of still a set of data array. And those array are fed into these kind of networks to pass them through a sequence of linear transforms and then integrate it with the physics property at each node, so that the predictions are still at those nodal values, but incorporates this kind of geometrical information and can be interpolated onto even a different structured graph structure, because those predictions are essentially geometry based. And it's actually the same for most operator regression models as for example, neural operators. They all do this kind of kernel integration that includes physics information at the front, but after integrating through the entire kernel, that stuff doesn't matter anymore regarding to the specific composition of that mesh, and it can be interpolated onto any variant mesh structure while still preserving the integrity of the solution. As for generalizability, the test that we currently did is able to perform within the Reynolds number range of 200 and 800. But as I said, the more generalization test that we did is actually towards interpolating onto any arbitrary resolutions. It's not really about changing the underlying physics, as it is essentially really hard if you never train the model on some kind of specific dynamics before, and then you want to generalize it these kind of scenarios. But we do have the potential of these kind of generalization in our second proposed method, as it's also what we're currently trying to do here, is we're trying to create this kind of comprehensive model library that are pre-trained and fine-tuned on various dynamics such as Reynolds number of 200, 800, 1,600, and then use this kind of pre-sorted classification. We then append various types of machine learning models to various types of physics that is probably unseen in the inference task, and to see how those will combine and interact with each other to make the machine learning model generalize better into unseen tasks in engineering fields.
One quick question. So on the domain decomposition side, is the main idea here just to treat each, like decompose the domain into separate tiles? Is that the core idea? Like essentially, instead of have one big snapshot, which is the entire domain, have like thousands of snapshots, which are individual squares?
Yes. So I guess the core idea.
Question, so sorry, just to complete my question, and then I see two hands up. So I didn't get how the time and associated with dynamics of that particular square is taken into account. So if you could clarify that, I appreciate it.
I probably didn't get your part about how the dynamics of that square.
So it's a turbulent flow. That single, domain is changing in time. You're treating it as one domain. I didn't see how you're incorporating the changes of that single domain in time.
Yeah, right. So if you consider it from this part, we're actually doing this kind of boundary impact. So as physics dynamics travels and hit the boundary of the previous decomposed section, they will be transported with this kind of separated learning effects into the domain of the next. So that completes this kind of dynamics. But for the training and learning phase, these are all down for 4 consecutive time steps, which are essentially pretty small, and most of the dynamics will stay within their assigned subdomains. And essentially what the core idea that we want to present here is that by reducing the scope that you are able to learn upon, you can actually improve the performance of networks, so that you don't need the whole data field to effectively train for a physics-based neural network. Essentially, that the network can learn better if you actually restrict the area. And we also developed theory for how to choose the size of that that makes the optimal learned dynamics.
Thank you.
Thanks for the questions. Maran.
Yes, thank you so much for the great presentation, as other people also mentioned. So I have a quick question. So when you do super resolution for the flow over the cylinder, I noticed that the super resolution results is quite different than the low resolution result. So how do you explain that difference? And I was wondering if you run the full order model with the super resolution discretization, which results would you reproduce, or would you be closer to the low resolution result or the super resolution result that you got out of the network?
You mean if you run Fourier neural operators?
No. Run the final element solver with the resolution.
Yeah, right. So definitely the super resolution model is designed to do this kind of dynamic correction. So kind of recover and correct for certain values that are miscomputed on the low resolution mesh. And we do have these kind of integrated solver examples. I didn't put it here. All right, yeah. I didn't put it here specifically, but we do have this kind of integrated solver loop where we, let me see if I have, where we do this process iteratively, that we feed low resolution mesh boundary condition physics into finite elements, grab an intermediate result, run through a numerical super resolution model, get a high resolution result, and then we interpolate this kind of process back, the refined model back into a low resolution mesh again, and do this kind of temporal loop that the results that we're able to get, we're only able to process the prediction loop for Burger's equation so far, but the result we're able to get from it is actually pretty stable. And what you are basically able to see is a machine learning model integrated with a numerical solver to form a new, more comprehensive numerical solver that consistently produces converged simulation results on a high resolution mesh. So I would say this process is really stable. And if you kind of interpolate the high resolution output from a machine learning model back to a low resolution mesh and then run recurrent finite element simulations onto that, this framework will still work.
Okay, got it. Thank you.
Actually, right on this same super resolution issue, would you get improvement if you took into account the previous temporal snapshot as well as the low resolution of the current time step? Have you tried doing that?
Yeah, that's a very interesting question. We've actually debated about whether to do this previously in our work, but we decided not to, as essentially we want machine learning model in this case to learn different things. So in this case, the model is not exactly learning the development of the physics dynamics. Right. It's rather trying to compensate for the missing dynamics on a low resolution mesh. But yeah, definitely, because we haven't tried it, so I can't say if it will exactly improve or worse the result. It's just, yeah, we didn't include that because we think those are learning two different stuff. But it might be interesting to try.
And another thing here, when you show the desired output mesh, do you include the high resolution boundary conditions in that? Or is it just the background mesh?
No boundary conditions is included in the desired output. It's just this process is just an interpolation.
Then you might get some if you have curved surface, you may get artifacts around that boundary. If you don't.
Yeah, so that is definitely an issue. As if you have curved surface, this kind of difference in resolution will definitely affect the result. But that is also very it seems to be really be handled pretty well in our test cases, but that is indeed an issue. And that's why starting from the second part, we're taking into account certain levels of boundary information, like regardless of the task. That is also what we're trying to do. Actually, what we're trying to do here, in this one, we're actually incorporating this kind of boundary effects. But I'm not able to show you the actual result here due to some kind of issues.
Yeah.
Thank you very much. I think there are no more questions. Yeah, thanks again for the presentation, Wenzhuo. Really appreciate it. I think it really resonated with the team. So I'm sure we'll have some follow-up discussions, hopefully.
Thanks, Danny.
All right. Thanks everyone for joining. Have a good rest of the day. Bye.